It's very important, guys, to note that a hyperbolic function is always given in the form of y, which is equal to a over x plus p plus q, right? It is always given in this form, right? Even when they give you a hyperbolic function that is in the form of y, which is equal to a over x, this is still in this form. Why am I saying that it's still in this form when we can clearly see that the equation written in green doesn't have a p and a q? Why am I saying that it's still in that form, right? Because we have a plus 0 there, okay? So technically, it is still in that form, right? So it's important to note that your hyperbolic function is always given in this form, guys. All day, every day, it's always given in this form, right? Even when they give it in the form of y, which is equal to a over x, you need to actually remember that there is a plus 0 there and there's a plus 0 there, right? And that plus 0 is our p and that plus 0 is our q. Okay, so a hyperbolic function, guys, is always given in that form, right? So let's discuss what all these variables mean, okay? So the a, guys, right? This a tells us about where a hyperbolic function is placed on our Cartesian plane, right? Okay, so the a tells us about our position of our hyperbolic function, right? What about this p? What does that tell us, right? The p gives us our vertical asymptote, okay? And what does the q tell us, right? The q gives us our horizontal asymptote. All right, okay. So it's very important to remember that the a tells us about the position of a hyperbolic function on our Cartesian plane. Our p gives us our vertical asymptote, right? And the value that is in the q position gives us our horizontal asymptote, right? So let's just look at the most basic type of a hyperbolic function that you guys can be given, right? For example, if they give you a hyperbolic function that is in the form of y, which is equal to 2 over x. The first thing you need to remember, guys, is that this is the same, right, as saying, right, y is equal to 2 over x plus 0 less 0. Okay, so let's start with the first point that I said, right? We said that the value of our a, right, in this case, y is equal to a over x, right? Our 2 is our a, right? Okay, so the value of our a tells us about the position of a hyperbolic function on the Cartesian plane, right? So if your a is greater than 0, that tells you that your hyperbolic function, guys, needs to be in the first quadrant and in the third quadrant. You need to remember that, okay? When your a is greater than 0, your hyperbolic function needs to be in the first quadrant and in the third quadrant, okay? That is your positive x-axis, right? That is your positive y-axis. That is your negative y-axis. That is your negative x-axis, right? Okay, so when your a is greater than 0, that tells us that your hyperbolic function is in the first and in the third quadrant, right? So that's the first quadrant, second quadrant, third quadrant, fourth quadrant. Done. Okay, and if your a is less than 0, right, that tells us that our hyperbolic function needs to be in the second and in the fourth quadrant. Okay, happy? All right, so we've actually discussed the first aspect of what I spoke about, right? About the a telling us about the position of a hyperbolic function, right? So in this case, because our a is 2, right, we can then deduce that, okay, our a is greater than 0 because 2 is greater than 0, okay? And because it is greater than 0, that already tells us that our hyperbolic function needs to be in the first and it needs to be in the third quadrant. We are done. Okay, so our hyperbolic function needs to be in the first, right? And it also needs to be in the third quadrant, right? So we've done that. Okay. Secondly, guys, I told you that the value of the p, right? Okay, because I spoke about the general form of a hyperbolic function being in the form of a over x plus p plus q, and I said that the p is your vertical asymptote, right? So your p is your vertical asymptote. So how do you get our vertical asymptote, right? You literally take this whole expression, x plus 0, right? And you need to solve it or make x the subject of the formula, right? So if you take that expression and you want, so it's x plus 0, right? And you equate that expression to 0, x plus 0 is equal to 0, and you solve, or you make x the subject of the formula, it'll be x, which is equal to 0 minus 0, where x is equal to 0, right? So the equation of our vertical asymptote, right, is x, which is equal to 0. So where is x, which is equal to 0, right? If that is our origin, our point 0, 0, right, that means our x, which is equal to 0, is that point there. Okay. So that red line there is our vertical asymptote, right? So that red line there is our vertical asymptote, right? And then, guys, I went on to say that the value of our q tells us about our horizontal asymptote, right? So what do I mean by that, right? In this case, our q is equal to 0, right? Our q is equal to 0, right? So if you get the equation of our horizontal asymptote, right, you're just going to take your y and it is equal to your q, right? And in this case, your q is equal to 0, okay? What does that mean? Okay, it means that the equation for our horizontal asymptote is y is equal to 0, right? And where is y equal to 0? That is where our y is equal to 0, right? Okay, so the red line is your vertical asymptote, right? And the vertical asymptote is your line x, which is equal to 0, right? And the blue line is your horizontal asymptote, right? Which is y, which is equal to 0. Okay, so we found our vertical asymptote of this particular function, right? Which is y, which is equal to 2 over x, right? We found the vertical asymptote. We found the horizontal asymptote, right? We have determined the position of a hyperbolic function, or where our hyperbolic function is placed on a Cartesian plane, right? And then from there, it becomes super easy for us to draw this hyperbolic function or picture how this hyperbolic function is supposed to look, because we already know that, okay, if your a is greater than 0, right, that tells us that the hyperbolic function needs to be in the first and in the third quadrant. We've done that. Okay, we found that, okay, we need to take this expression and we need to equate it to 0 to get the equation of our vertical asymptote, right? And we found the equation of our vertical asymptote to be x, which is equal to 0, right? And we also found that, okay, to get a horizontal asymptote, you need to say y is equal to the value of your q, right? And in this case, our value of our q is equal to 0, right? And then from there, we found that the equation of our horizontal asymptote, which is the blue line, is equal to y, which is equal to 0, right? And from there, we are happy. We've got our hyperbolic function, which is y, which is equal to 2 over x. Okay, let's just quickly define what an asymptote is, guys. An asymptote is a line that your function approaches, but it never touches. Okay, one thing about your hyperbolic function, your exponential function, they will approach your x-axis, but they'll never touch it, right? Especially your hyperbolic function that is in the form of y, which is equal to 2 over x. A hyperbolic function that has a vertical asymptote of x, which is equal to 0, and a hyperbolic function that has a horizontal asymptote of y, which is equal to 0, never ever touches your x-axis, and it never ever touches your y-axis, right? I'm sure you can see from here, this function is approaching. You see, it's approaching your y-axis, but it never touches it. It'll approach, like it literally approaches it, but it will never, ever, 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 ever touch your y-axis. All right. So the vertical asymptote is called an asymptote because your function never touches it. It never intersects your vertical asymptote. Same with your horizontal asymptote. This function will approach your horizontal asymptote, but it will never touch it. It will keep approaching it. It will keep it will even get there, but it will never ever touch that your line y, which is equal to 0. It will never. That is why it is called a horizontal asymptote. It's called horizontal because it is horizontal, right? And this one is called the vertical asymptote because it is vertical. All right. You are given the function f of x, which is equal to 2 over x minus 3 plus 1. All right. And from this function, I need you to tell me which two quadrants we're going to be working in. Right? I need you guys to give me the vertical asymptote and I need you to give me the horizontal asymptote, right? And once you've gotten the position of a hyperbolic function on our Cartesian plane, you've got the vertical asymptote and you've got the horizontal asymptote, I'm going to need you guys to quickly just draw that function on your Cartesian plane and show me how it looks, right? Give you guys 5 minutes to do that, right? And then just pause the video. Just quickly do that and then play the video. Just see how I tackle this problem. Okay, so let's get started. All right. So in this case, guys, still our a is greater than 0, right? So a is equal to 2, right? And your a is greater than 0, right? Therefore, remember, I told you if it's greater than 0, it is going to be in the first and in the third quadrant. All right, cool stuff. Number 2, to get your vertical asymptote, I said that you guys need to equate that expression to 0, right? So it's going to be x minus 3 is equal to 0, right? Therefore, your x is equal to 3, okay? And lastly, I said that you need to say, to get your horizontal asymptote, you need to say y. We know that f of x is also equivalent to, f of x is the same as saying y, right? So you say y is equal to that whole term there, right? Okay, please note that I've included the sign, right? Okay, because that is a term, right? So y is equal to positive 1. Let's quickly draw this function. Let's see how this function is going to look, right? Because we've already got our vertical asymptote. Okay, we've got our vertical asymptote and we've got our horizontal asymptote. So we're good to go. All right, let's see how this function is going to look. So the first thing that you guys need to do is obviously we draw a Cartesian plane, right? That's fine. Okay, we already know where the x-axis is and where the y-axis is, right? Okay, that is your positive y-axis, positive x-axis, right? Okay, we've got our vertical asymptote. Okay, our vertical asymptote is the equation x, which is equal to 3. So where is our x? Where is x equal to 3? So if you were to just add, that's 1, that's 2, that's 3, 4, 5 going on, 1, 2, 3 going on, 1, that's negative going on, negative 1 going on like that, right? Let's just put in the values. So that's 1, 2, 3, negative 1, 2, 2, that's 1, that's 2, that's 3, right? Negative 1, negative 3, okay? Negative 2, negative 3, right? Our vertical asymptote, this is actually going to show you guys why it's actually called a vertical asymptote, right? Because with the first example, it was actually hard for you guys to grasp what I was saying, right? With your basic hyperbolic function that is given as y, which is equal to 2 over x, because we just know that, okay, your vertical asymptote is 0, your horizontal asymptote is also 0, but you can't really, it's actually hard to grasp that concept if you don't have actual values there. If it's 0 and 0, it's very hard, it's very common that students would actually be confused about these asymptotes, right? But now that we've got actual values of negative 3 and positive 1, that'll help give you more clarity on what these asymptotes really are, right? Okay, so the first one, we said that your vertical asymptote is x, which is equal to 3. Okay, what does that mean? Okay, I'm going to do it in green. I'm going to do it in red. X is equal to 3. That is where x is equal to 3. X is equal to 3 there. Okay, that is where our x is equal to 3. Right? So that means that we need to draw a line going through or intersecting our x-axis at our point 3. Okay, what about our horizontal asymptote, right? And do you guys also see that this is actually a vertical line that is intersecting our x-axis at x, which is equal to 3. Cool, right? Let's go to y, which is equal to 1. Okay, y is equal to 1. We draw. That is our point. That is our point, y, which is equal to 1. Our y is equal to 1 occurs at point 0 and 1, where x is equal to 0 and your y is equal to 1. Right? And then if you were to draw the horizontal asymptote, horizontal because it is a line that is horizontal, right? Okay, that is our y, which is equal to 1 line. Okay, so that is your y, which is equal to 1 line, and that is your x, which is equal to 3 line. Okay, so what does this mean about our function? Are we still gonna say, oh, all right, okay, I'm a bit confused now. I know that my function is supposed to be in the first and in the second quadrant, and technically if I look at the green quadrant, that is the first quadrant, that is the second quadrant, that is the third quadrant, and that is the fourth quadrant, meaning that, okay, this graph is supposed to look something like that. Is that correct? That is absolutely incorrect. Okay, that is not how a graph is going to look. However, the new red lines that I've now included in my diagram, right, in our diagram, can also represent our new Cartesian plane. Right? So you can basically ignore the green Cartesian plane and focus on the red Cartesian plane, and that is going to be our new Cartesian plane, right? Because now that Cartesian plane will basically tells us that our function has moved 3 units to the right, right? That new Cartesian plane just tells us that the original function has moved 2 units to the right, which is 3 units to the right, which is 1, 2, 3, right? And it has moved 1 unit up, which is 1. All right, so we are basically dealing with a new Cartesian plane, right? And in our new Cartesian plane, our function needs to be in the first and in the third quadrant, okay? Because it is a value that is greater than 0, okay? So it needs to be in the first and in the third quadrant. So that is what the function is going to look like, okay? And that is going to be your new hyperbolic function, right? But yeah, we need to take into consideration then what the x-intercepts will be, because there will be an x-intercept, and what the y-intercept will also be, right? Because there will be a y-intercept. That our new hyperbolic function is intersecting our y-axis somewhere there and somewhere there. I can't really say that it's 2 because we haven't calculated that, right? So how can we get the x and the y-intercept of this hyperbolic function, right? So what we're going to do is, all right, you know that f of x is equal to 2 over x minus 3 plus 1. Okay, we're going to start off with getting what the x-intercept is, right? And to get the x-intercept, right, we need to let our y equal to 0, okay? And we already know that f of x is equal to y, right? So it's going to be 0, which is equal to 2 over x plus 1. And you just solve this equation for x. In other words, make x the subject of the formula. So it's going to be negative 1, which is equal to 2 over x minus 3. Okay, and then you just cross multiply. So it's minus 1 multiplied by x3, which is equal to 2. So it's minus x plus 3 is equal to 2. And solve for your x, guys. When you solve for x, you'll see that x is equal to 2 minus 3. Okay, therefore your x is equal to, okay, it's going to be minus x, which is equal to minus 1. Therefore, x is equal to 1, right? Okay, so if your y is equal to 0, your x is equal to 1, okay? So if your y is equal to 0, your x is equal to 1, right? So then that also tells us that we can just fix this here. Okay, so we already know that when your y is equal to 0, your x is equal to 1. So that is our x-intercept there, right? Cool, right? Let's go on to our y-intercept. Okay, and to get your y-intercept, guys, you need to let your x equal to 0, right? And if you let your x equal to 0, right, your f of x, which is equal to 2 over x minus 3 plus 1, right? F of x is the same as saying y, right? Which is equal to 2. Where you see x, you're going to put a 0 minus 3 plus 1, right? Therefore, you'll find that your y is equal to, just simply punch that into your calculator, 2 over 0 minus 3 plus 1, okay? You'll find that your y is equal to 1 over 3, right? So if your x is equal to 0, your y is equal to 1 over 3, right? And 1 over 3 is approximately equal to, this is equivalent to 0 and 0 0.333 recurring, okay? So if your x is equal to 0, your y is equal to 0 0.3333 recurring. Okay, so let's just fix that there. Okay, so if your x is equal to 0, your y is equal to 0 0.333 recurring. Therefore, guys, that is our exponential. That is our hyperbolic function. Okay, that is our hyperbolic function, right? That has the y-intercept 1 over 3 and the x-intercept 1. All right, and this hyperbolic function has the vertical asymptote, vertical being the vertical line, x which is equal to 3, and the horizontal asymptote, y which is equal to 1, right? Okay, and a value of a that is greater than 0, that tells us that we are in our new Cartesian plane, that is we are in a new Cartesian plane because we've got a horizontal translation and a vertical translation. So we are in a new plane, inverted commas, right? And that new plane, and in that new plane, we need to be in the first and in the third quadrant, right? And in the first and in the third quadrant, we are realizing that this function is actually intersecting our x-axis and our y-axis at a particular point. And to get the x and the y intercepts, right, of that function, guys, we need to let y, which is equal to 0, to get the x-intercept, and we need to let x equal to 0 to get our y-intercept. And from there, we are happy. We have got our hyperbolic function, right? So the main aim of this video, guys, is to show you guys that, firstly, an exponential function, guys, it's given in the form of y, which is equal to a over x plus p plus q, right? Even when your exponential function is not given in this form, but in the form of y, which is equal to a over x, you need to remember that there's actually an invisible or a 0 there, right? And a 0 there, which symbolizes or stands for the p and the q, right? Another thing that I want you to take from this video is that the a tells you about your position of your hyperbolic function, all right? If there is a 0 for your p and a 0 for your q, you just know that, oh, you've got your standard or your most basic exponential function, right? That is in your first and in your third quadrant, right? But the minute, right, you've got a p or an actual value for p and an actual value for q, in terms of maybe your p is a 3, 2, 1, whatever, and your q is a 4, 5, whatever, right? Then that tells you that, okay, that original hyperbolic function has been shifted a particular number of units to the left or right, or a particular number of units up or down, right? Okay, and therefore you need to get the equation of your vertical asymptote and your horizontal asymptote. And by getting that equation of the new vertical asymptote and your new horizontal asymptote, right, that will tell you what our new Cartesian plane is going to look like, right? And from the example that I used here, we could see that in this case, our new Cartesian plane was the red lines, right? And then we know that, okay, because our a was a value that is greater than 0, our hyperbolic function needs to be in the first and in the third quadrant of our red Cartesian plane, right? But then in this case, we notice, there's actually an x and the y intercept there. And to get that x and y intercept, you just need to let your x equal to 0, and you need to let your y equal to 0. Okay. All right, cool stuff, right? So guys, for now, I'm just gonna leave this video here, right? I'm just gonna leave this video here with just helping you guys understand those 3 points, right? In part 2 of this video, guys, I am going to show you guys, okay, how you define the domain, how you define the range of a hyperbolic function, right? And what are the lines of symmetry for your hyperbolic function. Okay, so please make sure that you watch a part 2 video of this. Please make sure that you watch part 2 of this video tutorial, because it will really help you guys with your paper 1, because they love asking hyperbolic functions. Okay guys, so I'll see you guys on my next upload. That is it, guys, and I'll see you guys on my next upload, Distance Learning with Lee, where I make learning mathematics super easy. Bye guys.